Hi, this video is Chapter 12, Section 3, and our objectives here today are to differentiate between harmonic series of open and closed pipes, calculate the harmonics of a vibrating string and of open and closed pipes, relate harmonics in timbre, and relate the frequency difference between two waves to the number of beats heard per second. Okay, so let's see this video.
On a given string of length L, standing waves exist only at certain wavelengths and frequencies. The lowest frequency at which a string can vibrate, called the fundamental frequency, is determined by the fact that the string is held fixed at its ends. The fundamental frequency of a vibrating string is produced by a standing wave that has a wavelength twice the length of the string, as shown here. Other standing waves that can be supported are simply integer multiples of the fundamental frequency. The sound of an instrument, such as a violin, is due to many of these frequencies being present when a note is played.
Okay, first of all, you probably don't need to see my talking head anymore, so I'm going to get rid of that. There you go. All right, any string that vibrates can contain many different waves. Each one of those has a different wavelength and different frequency. The greatest possible wavelength that you could have on a string, and by the way, this string could be a piano string, it could be a violin string, a cello, any type of string like that, or it could be, something even different. It could just be a string in a science laboratory. But the largest possible wave you could have, or wavelength, is 2L. In other words, twice the length of the string. The fundamental frequency is the frequency that corresponds to the lowest frequency of vibration, and that is where that wavelength is 2L. And you can see this by in this diagram here. When you have a node at each end of the string, one big loop in the middle. Remember, this is this wave is actually reflecting off of this node, off one of these nodes, and bouncing back. And so you have half a wavelength here, the other half of the wavelength there. So the total wavelength is twice the length of the string. That gives us the equation for the frequency, solving V equals F lambda for the frequency. We get frequency equals V over lambda 1, and since that fundamental frequency is 2L, V over 2L is the fundamental frequency.
The harmonics of any vibrating system are the frequencies of the standing waves that can be formed by that system. The first harmonic is the lowest frequency and is produced by the standing wave that has the longest wavelength, which is 2L. The second harmonic is the next lowest frequency and is produced by the standing wave that has the next longest wavelength, which is L. All the harmonics of a system have frequencies that are integral multiples of the fundamental frequency.
Okay, each harmonic in this situation then is going to be an integral multiple of the fundamental frequency. So a harmonic series is a series of frequencies that includes the fundamental frequency and then integral multiples of the fundamental frequency. Now you'll notice it does not say all integral multiples. There may be some integral multiples that are not included. And so we get the general equation, F sub n equals n times V over 2L, where n is the numbers 1, 2, 3, and so on. 1 would be the fundamental frequency, and then all the rest of those would be the other harmonics in that series. Okay, so it's equal to the harmonic number, 1, 2, 3, and so on, that's always an integer, times the speed of the wave divided by twice the length of the vibrating string. And so here you see a graphic representation of the um, first the first four harmonics in a series where n equals 1 in this case, 2 in this case, 3, and 4. And this formula should look familiar to you. But in this case, the wavelength is 2L. Here it's L, 2/3 L, 1/2 L. Okay, so it comes out to be 2L over N is the general formula. So here 2L over 2 gives you just L. 2L over 3 gives you 2/3 L, and so on. Okay, and the second harmonic, F2, is equal to, in this case, twice the frequency of F1. And you can see that here. 3 times the frequency, 4 times the frequency, and so on. Pipes can, we have two situations for a pipe. One of them is when both ends are open, and one is if one end is closed. When both ends are open on a pipe, both of the ends are antinodes. And in this case, all the harmonics are present, and the equation that we just saw would be the equation that would give us the harmonic series for air in a vibrating air in a column. So for the pipe open at both ends, you have the harmonic number times the speed of sound in the pipe over twice the length of the vibrating air column. Okay, and this generally is the length of the pipe. You can sometimes have to make small adjustments for the diameter of the pipe, but for the most part, this will give you a good approximation of what you've got. If one end of the pipe is closed, then there's going to be a node at that end and an antinode at the other end. Okay, in that case, only the odd harmonics are present, only 1, 3, 5, 7, 9. Okay, so here our number doesn't go 1, 2, 3, it goes 1, 3, 5, 7, 9, and so on. So it's just the odd harmonics that are present. The evens can't occur in this situation. And here you see some examples of that. We won't go through all of these, but A represents antinode, N represents node. And so you can see you can have, in a closed pipe, you can have an antinode at one end and a node at the other. This is your frequency. With a open pipe, you have an antinode here and an antinode here. And that gives us the fundamental frequency. And again, as you go on, where you have antinode, node, antinode, node, antinode, you get the different harmonics present. Here you have F1, F2, F3. If the pipe is closed at this end, you have F1, F3, and F5, because you cannot have an antinode at this end. You have to have a node. Okay? So that's the difference between open and closed pipes. Okay, so we're given the sample problem. What are the first three harmonics in a 2.45 meter long pipe that is opened at both ends? What are the first three harmonics when one end of the pipe is closed? Assume that the speed of sound in air is 345 meters per second. So we'll look at the solution of this. Here you see the given information and the unknowns that we want to find. Again, in the second case, over here, the pipe is closed, so we have harmonics 1, 3, and 5. With the open pipe, we have harmonics 1, 2, and 3. Okay, and we will use then the equation given here F sub n equals n times V over 2L, where n is equal to 1, 2, 3. F sub n is equal to NV over 4L, where n is 1, 3, 5. So these are the first three that we'll look at. And you can see here that once you have found that fundamental frequency, you can get the second and third numbers by simply multiplying. There's no point in doing this arithmetic anymore, so you can just multiply by the harmonic number 1, 2, and 3 in case 1, 1, 3, and 5 in case 2 to get those harmonics. Okay, so in case 1, we find, just by substituting in the values, we find that the frequency is 70.4 hertz. So the next two harmonics would be 70.4 times 2, or 141 hertz. Watching out for our sig figs there. And the third harmonic would be 211 hertz. Again, notice that we're paying attention to sig figs there. In case 2, again, it's just a matter of substituting numbers in, and we come up with a frequency, a fundamental frequency of 35.2 hertz. And then the third and the fifth are gotten just by multiplying that by 3 and by 5. And again, pay attention to sig figs here, and you get 106 and 176. And then they evaluate that, and I'll just give you a second to read that. Okay.
Each musical instrument has its own characteristic mixture of harmonics at varying intensities. A tuning fork produces a pure sine wave with no harmonics. A viola string playing the same note as the tuning fork produces several harmonics, as shown in the graph. Each harmonic is itself a sine wave, and they add together to form a resultant waveform. The presence of these harmonic frequencies in the vibrating viola string produces a more complex waveform than that of the tuning fork. The difference in the two waveforms causes the tuning fork to sound different from the viola, even when both instruments are playing the same note at the same volume. Because the harmonics of musical instruments vary from instrument to instrument, every instrument has a different sound quality. This sound quality is known as timbre.
Timbre is the quality of a tone resulting from a combination of all the harmonics present at all their different intensities. All right, and this is why the different instruments sound different. A clarinet and a viola, or in the case that in the animation we just saw there or heard, the viola and the tuning fork, or the violin and the tuning fork, sound different because they have different timbres. The harmonics of most instruments provide a much fuller sound than a tuning fork, and you hear that with any musical instrument. When somebody plays a note on it, it just sounds more complete than a tuning fork. A tuning fork is very empty, if you will. Here you see the example. A tuning fork gives you a single frequency, one wave. It's a sine wave. The clarinet gives you a sound like this that's the result of adding together all of these different frequencies and their intensities. A viola or a violin sounds even different from those because of its different frequencies, the harmonics, and so it has a different sound than either of those two. You can usually tell the musical instrument, if you're familiar with it, simply by its sound, by its timbre.
When two waves of slightly different frequencies are present, they can interfere. The interference pattern varies in such a way that a listener hears an alternation between loudness and softness. The variation from soft to loud and back to soft is called a beat. One beat is shown here. When the two waves are exactly out of phase, destructive interference takes place. The two waves cancel each other out and there is little or no sound. When the two waves are exactly in phase, constructive interference takes place. The two waves add to a large wave and there is a louder sound. As the sound continues, the waves continue to produce destructive and constructive interference, giving beats. Piano tuners use beats to tune piano strings to a reference note from a tuning fork.
Okay, so when you, as you just saw there, when you have beats or waves of slightly different frequencies, the interference pattern will vary in such a way that you get beats, areas or alternations of loud and soft tones. Those are called beats. So a beat is the periodic variation in the amplitude of a wave that is the superposition of two waves of slightly different frequencies. That is kind of a complicated way of saying that it's actually the difference in the two frequencies that tells you the number of beats per second that you'll get. For example, if you have one wave that is at, let's say, 239 hertz, another one that's at 240 hertz, where they coincide here, where crest and crest coincide, you're going to get a much larger wave. Where the two troughs coincide, or a crest and a trough coincide, you get the sounds canceling out, the waves cancel out each other, you get destructive interference there, and so you hear nothing. So it goes from nothing to very loud, back to nothing again, and the number of these that you get per second will be the difference in frequency of the two waves. So if you have waves of 239 and 240, it would take 1 second to go from soft to loud to soft. Okay. Normally, if you're counting these, you're going to count from the loud period. So from the period of loudness to softness to the next loud would be the same thing, 1 second, if the difference in frequency is 1 hertz. Okay, let me show you how, or let me allow you to hear what beats really are. I'm going to use a GLX simulator. This is just like the GLX that you'll be using this week to do some similar experiments. We're going to use the output part of this. And right now this is set to give us a sine wave of a frequency of 440 hertz on both the left and the right channels. So if I turn on the left channel, you hear the 440 hertz signal. If I turn on the right channel, you hear both channels at 440 hertz. Now, if I change one of the channels to 441 hertz, you'll hear beats. You hear 1 beat per second because the frequency difference is 1 hertz, and so that gives us a beat of 1 per second. If I change this one to 442, that's a difference of 2 hertz, and you now hear 2 beats per second. If I go and change that to 443, you now have a frequency difference of 3 hertz, and you hear 3 beats per second. So it's the frequency difference that gives you the number of beats per second, assuming your beats are in hertz. Now I'm changing this one back to 439, and again, the difference is 1. You hear 1 beat per second. Change it to 438. You now hear 2 beats per second. and 437, you now hear 3 beats per second. Notice that you cannot tell whether one frequency is higher or lower than the other. You can simply tell the difference in the number or the difference in the frequencies. So we know if we're hearing 3 beats per second that there's a frequency difference of 3 hertz, but we can't tell if it's the 440 plus 3 or the 440 minus 3. It could be either one. And that ends this session of our for physics. Thanks for listening.